The last topic we will cover as we talk about charge stabilization is hyperconjugation. Now, hyperconjugation, we won't use it much, perhaps not at all, in explaining acid-base chemistry. However, it's really commonly used in discussing the stability of carbocations, which are a charged species. So let's look at some different carbocations, and then we'll bring up how hyperconjugation plays a role here. Here's a carbocation. This is called a methyl carbocation. It's supposed to be a plus in that circle there. Let's fix that. This is referred to as a primary carbocation. It's a primary carbocation because the carbocation, the carbon with the charge, bears one carbon group, so it's considered a primary. The one group, it's primary. Now, if we have two carbon groups dangling off of the carbocation, it is called a secondary carbocation. And then lastly, if we have three groups, which is our max, then this is a tertiary carbocation. And they call these primary, secondary, and tertiary. And even though we write one with a degree sign, you don't call them a first degree or second degree. They're called primary or secondary, even if you write the number with the degree sign. So, methyl, primary, secondary, tertiary, these carbocations have different stabilities. As it turns out, the methyl is the least stable, and the tertiary is the most stable. So how do we explain this stability trend? Well, we explain it through hyperconjugation. Note that we're not talking about acidity and basicity here, but we are talking about stability of a charged species, a carbocation. So here's how people explain this. Let's draw out our primary carbocation. Our primary carbocation is sp2 hybridized, and that vacant lone pair, vacant p orbital, is on our carbon. So let's draw this sp2. I'm trying to show this is trigonal planar. So apparently that vacant p orbital is not very well stabilized. This is the least stable structure. As we go to a primary structure, there are a couple different ways to show this. I'm going to select one, stick with it. This is still an sp2 hybridized carbon, but what you find is this group, this added group, helps stabilize a positive charge. And a way people explain this is they say, well, it's this CH bond, the neighboring CH bond, because remember, this is a bonding pair of electrons. This sigma bond is able to weakly overlap with our p orbital, and the filled sigma bond stabilizes the vacant p orbital. And so this carbon feels a lack of electron density, but that lack is alleviated somewhat by this carbon next door with its CH bond. And you can imagine if you had two carbons attached, as we have in the secondary, you get even more alleviation of the lack of electron density on the carbocation. And then if you have three attached groups, you even get more alleviation. So the carbocation becomes more and more stable. These are mismatched orbitals. They don't have the same shape. A p orbital and sigma bond don't have the same shape. Yet they are able to weakly interact and give an observable difference in stability. The tertiary carbocation is quite a bit more stable than the methyl carbocation. And so it's this mismatching of orbitals, or mismatched orbitals that are trying to overlap, that are our hyperconjugation phenomenon. So hyperconjugation involves overlapping mismatched orbitals. You don't get a super strong effect, but it is an observable change in the stability of these cations.